Okay, okay. So we are back in business. So just a few notes. I had some questions about the assignments. The date of the assignment is basically the last day of the course. And because of my time zone, I think the last assignment was showing as 18. So it's basically on Friday. You kind of need to be done. So that's, if there are any questions, ask Professor Ambika for, but because I'm not dealing with that, but as far as I understand, it's, and from that perspective, we could have different deadlines for different assignments. I just thought it was easier to have them all at the end. So that's, then about getting the assignments. And so I also shared the lecture slides for what we did until now. So again, hopefully most of you have received those. Hopefully those are going to be useful. I also, but if you have not received the emails with the assignments, and if you have not received the lectures yet, there was something weird about the way you had your email address in the spreadsheet. So after, so right now I'm going to show a few more slides to help with the assignments, with the last assignment, with the third one. But then I'm going to sit down with some of the IIT Jammu students and figure out the email thing. I guess some of these comments apply to the people online. If there are any questions online, I hope, again, someone is monitoring the chat. And the other thing is that there were some questions about, why is this kernel that large? Why are there those channels? There is an area of research that deals with that. So again, at the beginning of, when AlexNet was done and all that, it was a bunch of students like you in the lab of the professor at the time. I think it was Jeffrey Hinton, who got a Nobel Prize for this, by the way. Doing kind of trial and error and figuring it out. And, and in many ways, that's still kind of the way it happens. If you look probably at how OpenAI is doing the GPT-5 or whatever they are working on right now, there's still a lot of trial and error. There's no real science. I mean, there is some science, but, it's hard to automate. But the field of trying to automate that has a name. It's basically NAS, N-A-S, network, I guess, architecture search, NAS, network architecture search. So if you Google that, there is a Wikipedia page. There are tons of papers on Google Scholar about NAS, about how to optimize these networks. And again, people are working on automating them, but it's still, debatable how well it works. Okay, so the current assignment, the third assignment, is about training, and it uses GPUs as well, because for training you kind of need to use GPUs. So we already talked a little bit about training, before lunch, but now I want to talk a little bit about GPUs and how they work. And again, just to remind everyone, at the end of the day, this is all we want to do. We just want to be able to do very efficiently. Batch normalization, I see a question online. So again, the goal of batch it's all about the efficiency of training. And that's kind of a very generic answer. All those techniques that are being done are to optimize the training, to basically get the training to converge faster. So batch normalization is one of those, and there are many other techniques that are being used. So these are kind of the fundamental deep neural network operations, and the ones that we are going to focus more are the vector matrix, and fundamentally this is a very parallelizable type of operation, because you have all these for loops, and we already talked about the Flint's taxonomy and about Amdahl's law. So again, these are important to understand these concepts that come into play with GPUs and CPUs. So again, another important kind of concept has to do with performance. And when we talk about performance, two types of performance metrics come into play, and those are latency and throughput. Can someone help me with latency and throughput? How would you define latency and throughput? One at a time, just whoever. Yeah. Okay, and throughput? Okay. So is there a relationship between latency and throughput? Okay. Okay. So in the simplest case, throughput is 1 over latency. Okay. Can you have throughput higher than 1 over latency?
It's possible.
How do you do that?
Maybe we can.
There's a magic word. I just want one magic word.
Can use parallelism.
There is a special type of parallelism. Pipelining. Thank you. Yes. So pipelining. So parallelism in time. Right. So fundamentally, this is, throughput is always going to be, higher than 1 over latency, hopefully. What you really want, and this is a key to these AI systems and AI algorithms, you really need throughput to be much, much higher than latency. Because, if throughput is equal or, very close to 1 over latency, the performance is going to be terrible. So this is another reason why GPUs are winning this race. Because CPUs are really optimized for what's called single thread performance. So I basically run one program. I'm there at the terminal, I'm typing, and I want the results to be very close. So they are really, optimized for low latency, and you need that as a user interactive. But because they are, optimized for low latency, designing a CPU, you spend a lot of resources to get that low latency. And again, we already went over this, but now, I'm kind of presenting it in a different way from this concept of latency and throughput. On the other hand, GPUs have terrible latency. They are really very bad in terms of latency, but they have massive throughput. And at the end of the day, that's what it matters, because, these computations, last minutes, hours, days, weeks, months. So you don't really care about latency if instead of, 3 months is 3 months and a week, if the throughput is twice larger and, you run twice as many, computations. So that's really again, another key thing. Now, a little bit, you saw that I like to present a little bit of history. So a little bit of history of GPU. So GPUs were done for graphics, for games. And, there were all these kind of different, very special purpose kind of, there was a pipeline, even at the time, obviously, throughput was very important. But the pipeline was, had different, vertex, rasterization, fragments, things like that. And what's interesting is that for graphics, they already started to unify the architecture. So instead of having, 4 different custom special purpose pipelines, they created this what they call the unified architecture, where they just had shaders that were programmable, and those could be programmed to do any of the, of these kind of functions. And, this happened before AI, but it worked very well because now suddenly these shaders became much more general purpose instead of being just for graphics. So again, in terms of progress with the architecture, an important, it's, in retrospect, it sounds pretty trivial, but it was a pretty, again, important to have this concept of a fused multiply and add function. So CPUs, do a multiply, you fetch the instruction, you do the multiply, then you fetch the instruction, you do the add, and that, again, is more general purpose. But, if you just want to do a lot of multiply and adds, you are better off fetching just one multiply and add, you do the operation, and then you're done. And that also an important feature is that it saves on the rounding. All these multiply and adds were in the floating point. Rounding in floating point is expensive, so you save one of those steps. Again, that was 2010, 2017. We had already 21 billion transistors, so that's pretty impressive. 12 nanometer FinFET, TSMC state of the art at the time. You had this, basically streaming, cores, which basically you had, 5,000. And again, there was the discussion about CPUs and concurrency and all that. So, you have 5,000 basically processing units that, compete against maybe, the most complex CPU nowadays maybe has 64 cores. So, this is 2 orders of magnitude more. Only 80 of these were active. Why do you think that was the case instead of 84? Yeah, very good. So yeah, you have yield issues, right? So this is a very complex chip. Yield is not going to be 100%. This way they could, turn off some of those elements and, sell them. Yeah.
Shader architecture and the code that is just stored in the Volta's architecture, the NVIDIA Volta.
There's no difference.
They're exactly same?
Well, no. I don't know. There are, fundamentally, there's no difference, but I'm sure, again, going 7 years, they definitely had, I don't know, but it's certainly different technology. I mean, this was probably, 65 nanometer, maybe bulk. That's 12 nanometer FinFET. I don't know. But they were all, I mean, again, they were still 32-bit, 64-bit. That only changed later. I think they were basically very similar. I don't know. A little bit about, and again, I should also preface this. So I had some questions about a student about, FPGAs and HLS, and I want to address that. We are not, well, maybe I'll have a few slides about that. The plan initially was to have, hands-on with that, but we figured out that with that many students and with a very diverse kind of background, it would be really hard to manage. Again, dealing with hardware is also harder than with software. But the other thing that, was kind of promised was to have, GPUs and CUDA. And I'm going to have a few slides about CUDA. Now, good news or bad news, is that the hands-on, because we are going to use PyTorch and NumPy and all that, CUDA is there when you run on a GPU, but luckily you don't have to see it and program it, because that would be kind of very hard in the time that we have here. So, but we are going to talk a little bit about CUDA in the slides. So again, this is kind of the single-threaded execution model. And this is typical CPU execution model. And this is a typical GPU kind of execution model in which you basically execute things in parallel. I shouldn't say GPU. So this is a SIMD. This is a parallel execution model, in the generic SIMD, single instruction, multiple data concept. You will see that for GPUs, it's slightly different because you do what's called single instruction, multiple threading. So there is this concept also of single program, multiple data. And this is really closer to how GPUs work. And the idea here is that you can still have some difference in execution between for different data in your array, but it's not a control. It's really more of an arithmetic kind of decision. In other words, for example, if the number is larger than a threshold, then you do something. If it's not, you do something else. They still execute the same instructions, so same programs, but you have this difference. It's much simpler to do than real multiprocessing. So basically, these are kind of the three models. So you have the single thread. This is the single processor multi-thread, and this is multiprocessing. And the big difference is here, where you really have different code. So each processor executes a different kind of program. Here, you share the kind of the global instructions together, and the only thing that's changing for the different processors is the local thing, their register file and their stack and things like that. And if there are any questions, let me know. So this is the single instruction multi-threading execution. So, and again, there is a terminology that NVIDIA uses for GPUs, and frankly, from here to the end, is this NVIDIA terminology. And if you read the Hennessy and Patterson book, they are complaining that NVIDIA basically has reinvented terms and is using terms that have synonyms in the conventional computer architecture, but they use different terms, and that creates some confusion. But so they use this concept of warp, where they package together a number of threads, 32 threads in this case, and they all execute the same instruction. So again, the advantage is that you have the same fetch and basically dispatch. And when, again, this is when the code diverges, this is the equivalent of the previous slide. Some of them basically become inactive. And this is done on, so that's the nice thing from a programmer perspective, that this is done by the hardware. And again, this is a choice that they made on purpose so that they can do more computation in the trade-offs. so in the same amount of silicon. Um, but again, so this is important too. If you are completely oblivious to this, probably your program is going to give you the right answer, but it's going to run poorly. So you still, unfortunately, need to understand this for performance. So again, in terms of, and I do want to go pretty fast because again, assuming that you have something like this where two different branches have a common part, then there is maybe like an if. So the two branches diverge and then converge back. If you did this, kind of in a single path, you would first need to kind of execute this and then execute that. The nice thing with the way GPUs do, they can basically interlace some parts from one to the other. And again, this actually reduces latency in this case, but automatically also improves throughput. So this is an interesting kind of representation of something somewhat related to Amdahl's law. So basically, again, remember Amdahl's law on the x-axis had the number of processors, and on the y-axis it had the performance, and there was something that looked like that, with basically having at the beginning with the number of processors, the performance goes up, but then it plateaus. What's interesting with GPUs, and again, this is slightly non-intuitive, and this is not exactly like Amdahl's law, because on the x-axis you have the number of threads. So it's not the number of processors. So the number of processors is fixed in this case. But you have this interesting phenomenon where this is very similar, let's say, with what you'd expect in Amdahl's law. So as you increase the number of threads, the performance goes up. But then you have a valley here, and only starts going back up when the number of threads is much, much larger than the number of processors. And the way to understand this is that, at the beginning, when the number of threads is less than the number of processors, then, it's very easy. You just, the performance goes up with the number of threads directly. But then when the number of threads is close to the number of processors, there are many conflicts where, threads are not ready. So there is a lot of waste, processors that cannot be filled with threads because, most threads are maybe doing something else or waiting or something happening. But then when you have more and more threads, at some point, there's always going to be some thread waiting that you can schedule on the processor. And only here, you basically end up, this is the Amdahl's law, limit. So all the processors are basically busy all the time. But that happens only if you have, a massive amount of threads. So that's kind of an important thing. But that's helpful for AI. Because in AI, because we have all those computations, there are so many computations that basically you are always working here. And that's a good thing. So the GPU doesn't in terms of
Dividing the given program into the number of threads, is it done by the CPU, and who is scheduling everything?
Yeah. So that's the CUDA thing. Yeah. That's the whole CUDA. So it's the programmer. So yeah, and you can say it's the CPU, but it's really the program that you are writing. The program, Yeah. Yeah, exactly. Yeah, yeah, exactly. Well, it's not the operating system. I don't think the operating system has, yeah, there is a scheduler with the, um, yeah, it's basically the driver. So NVIDIA has a driver. So there is some OS thing, but it's not OS in the way it would do it for a CPU. Yeah, I'm not an expert on that, but so this is how it looks like for a programmer, how the GPU looks like for a programmer. You basically have your CPU, your main memory, and then you have your GPU, and you have the GPU memory, which is separate from the, and that's another reason why the OS is not really scheduling, from the GPU memory. So, so this is actually a pretty narrow pipe in between these two memories, and the memory, I should say that AMD has come up with new architectures where the CPU and the GPU share memory space, and so this is not the only thing, but especially for very large GPUs that are used massive amounts, you actually do want them to have separate memory. There is a price to pay to go back and forth between the two memories, but given then the computation can be much more efficient. So and again, I would like to wrap up pretty soon, but basically this is how how the scheduling happens. So you first need to copy the data from the CPU to the GPU memory. Then you launch these threads that we've been talking about. And then you basically, there is still something going on the CPU, so there needs to be some synchronization at some point. And then, once the computation is done, you copy back the data and you move on. And again, there is this hybrid execution flow. This is basically showing kind of the same things, but now more in terms of the, a little bit more the architecture part. Here is where, again, NVIDIA adds some terminology and some complexity because these threads are organized in blocks. So there is a hierarchy of these threads. So it can get quite hairy, but again, there are some blocks in grids, and inside each block there are threads, and again, the programmer in principle can have very fine-grained control, and many, again, the NumPy libraries and all that, that's how they optimize for high performance. They basically spend a lot of time in optimizing these kinds of details. Yes. Yeah, you don't, for better or for worse, again, yes, no, you will not see any of this. But again, it's good to know that it's behind the scenes. So this is, and this comment I think is important because NVIDIA right now, like we mentioned, is the most valuable semiconductor company in the world, and ironically, it's not because of the hardware, or it's not just because of the hardware. It's really because of the software. So they basically enabled programmers. I mean, their hardware is pretty good, but if it was just hardware, there would be many more competitors, and they wouldn't be so dominant. But they are really dominant because this CUDA thing that basically is pervasive. And you may have heard this term, but this creates a moat. You've heard this term, a moat? So from a business perspective, in the old days, moats were around castles or forts to basically keep the enemies away from the fort. This is a business moat because having CUDA keeps the competitors from competing with them. but yeah, so there are all these libraries and, then this CUDA driver that I was talking about is important. Again, I'm not going to this will take, but I'm going to share these slides with you as well, so you can spend some time. But basically, again, CUDA has won because, CUDA has been introduced 20 years ago, roughly, I guess. It looks like C. So it's basically an extension of the C program, which was, kind of the most popular at the time. And again, you have these special, instructions, CUDA memcopy, which does the copy from, the CPU memory to GPU memory, CUDA malloc, which, allocates space for the arrays and all that. Yeah, so this is how basically a CUDA application looks like. You have a compiler, which is this NVIDIA C compiler. You have a combined CPU and GPU code, and basically you have the GPU part and the CPU part, and then you get this CPU GPU executable that you run, and some commands on how to do the compile. And yeah, sure.
In the assignment 2 itself, there was a question where we had to rescale and resize the images which needs to be fed into the BGG model basically.
Yeah.
So that particular part, it comes under the pre-processing. So that happens on the CPU side, or where does it happen?
Yeah, I think that happens on the CPU. I'm not 100%. I'll have to look at the assignment to see. I'm pretty sure, because that's not, resizing images is not computationally expensive, I think. Probably it happens on the CPU. Yeah, I would guess it happens on this.
NVIDIA now also has a CPU in their board. So does the operating system also host there, or there's a separate computer where the operating system hosts?
No. No, this is under the operating system. So there is this CUDA driver that works under Linux, basically. Yeah. So it's part of that. So so what's your real question? Maybe there is another question behind that question. Sure. No, this is still a computer that runs an OS, and yeah, you still need an OS, but this combined CPU, GPU executable runs under that OS. So yeah. I'm not going to spend again, here is how these blocks, fit on the resources. It's just too much. But the important thing, and again, that's another reason why CUDA is so dominant. CUDA works perfectly well on any of these without recompiling or anything like that. So basically, the architectures are, compatible 100%, and there were some questions, what's the difference between this and that? That's another, kind of reason there is no difference. Yeah, and again, some more about these grids. I'm not going to, there are some extensions to the C code. I do want to, again, some more CUDA malloc. So this is from the Hennessy and Patterson, and with this we are really done, and you can start working on the assignment. At the end of the book, they have this table in which they, have the kind of the concept, then the conventional nomenclature, and then the NVIDIA nomenclature. And, like everything that we've seen until now, so grid, came up, that's a vectorizable loop. Then, CUDA thread, it's an iteration of a scalar loop. This warp thing is a thread of vector instruction. You know, they have this PTX instruction, which is really just a vector instruction. And then, you know, there is, you know, streaming multiprocessor versus vector multiprocessor. They use giga thread engine instead of scalar processor, you know, warp scheduler. Yeah, so you can see, you know, global memory versus main memory. So they basically named almost every concept that related to what they were doing. Okay, so with this, we are done. I was hoping to be done.